The Doppler effect is more present in the world than I ever fully realized. If you just look at the formula, it can seem confusing. The Doppler effect was discovered by Christian Doppler in 1842. The equation is F sub naught equals F sub S times the quantity of V plus or minus V sub naught, all divided by V plus or minus V sub S. In this equation, F sub naught is the frequency of the sound by the observer, F sub S is the frequency of the sound waves, V is the speed of the sound waves, V sub naught is the velocity of the observer, and V sub S is the actual velocity of the source. Knowing the equation is helpful, but that doesn't explain what the Doppler effect actually is. In actuality, the Doppler effect is a very simple concept to understand. In essence, it is the idea of how waves move with respect to an observer. When a sound is moving, it sounds like it reaches a higher pitch as the sound gets closer to the observer. As the sound gets further from the observer, it sounds as though the pitch gets lower. One important thing to note, though, is that there is not an actual change in frequency. In the demonstration, you will hear a monotone sound and how it appears to change as it moves through the air. However, it does not only apply to sound waves. The Doppler effect can be seen in waves such as water and light as well. In this slide, you will see a demonstration of the Doppler effect. All you need to replicate it yourself is a JBL speaker, a cord of some sort, and a sound. For my demonstration, I used the sound of 432 Hertz.
Go.
Okay, so using a JBL speaker, my Apple Watch charging cord, and a sound of 432 Hertz, I'm going to show you the Doppler effect. So this is what it sounds like. So he's going to think I'm setting off a fire alarm. Now watch or listen to what happens as I start spinning it around. It's so natural for me. You hear the sound changing? Now, if we go this way, different sounds are happening. And that is the Doppler effect. Cool.
In this demonstration, you heard how the sound seemed to change as the speaker moved through the air. An easy example to better understand the Doppler effect is to imagine a bug in the water that is moving its legs to stay afloat. The movement of the bug's legs will cause ripples in the water. Two specks, which are of equal distance from the bug, will experience the ripples hitting them at the same time. However, if one speck is moved closer, it will be hit faster and more often than the other speck, which is further away. This can be seen in the two pictures to the side. Perhaps the easiest example to understand is that of a siren. When you hear a siren outside, it sounds louder and the pitch also gets higher as it draws closer to where you are. As it gets further away from where you are standing, the frequency gets smaller, which causes the pitch to get lower. A person who is further away from the siren is experiencing a long wavelength with a low frequency, whereas someone who is standing closer to the siren is experiencing a small wavelength and a high frequency. This can be seen in the picture. Another example is found in audio, especially at concerts, radars, and in blood flow management. Imagine a train that has a 150 Hertz horn that is moving with the speed of 35 meters per second with a speed of sound of 340 meters per second. What are the frequencies observed by a person who is standing still as the train approaches and as the train recedes? What does an engineer on the train experience in terms of frequencies? To solve, we plug in the numbers into the equation. This leaves us with an F sub naught equals 150 Hertz times the quantity of 340 meters per second divided by 340 meters per second minus 35 meters per second. This means that as the train approaches the observer, there is a frequency being emitted of 167 Hertz. As the train recedes, we can get the equation to read F sub naught equals 150 Hertz times the quantity 340 meters per second divided by 340 meters per second plus 35 meters per second. This leaves us with a frequency of 136 hertz. To an engineer on the train, the frequency experienced is 150 hertz. This is because the velocity between the engineer and the train is 0 meters per second. So we get F sub naught equals 150 hertz times the quantity of 340 meters per second divided by 340 meters per second. Since the velocities in the numerator and the denominator cancel out, we are left with 150 hertz, which is the original frequency. In this case, F sub naught equals F sub S. So what does the Doppler effect actually tell us, and how is it useful? Astronomers use it to measure the speed at which stars and galaxies are either approaching or receding from the Earth. Cops use radars which rely on the Doppler effect to detect the speeds of passing cars. You can thank the Doppler effect for any past or future speeding tickets. The medical field also uses the Doppler effect to measure the velocity and direction of blood flow. The Doppler effect is an easy enough concept to understand once it is made clear how often it appears in our world today. The equation looks intimidating, but don't let that fool you.